Okay, share. All right, and then, so, maybe it's here, cool, okay. All right, so while I'm still having people kind of filter in, how, just out of curiosity, how did you guys find Project One? Was it reasonable? Was it like good amount of work, too much work, too little work? Kind of how did you all feel about it? Okay,
Yeah, I agree. It was pretty reasonable.
Okay, I'm seeing some reasonables. Anybody not a fan? Okay, so it seems like, okay, so nobody was hating on it too badly. And just out of curiosity, kind of, because again, as I have now stressed multiple times, the idea for this was obviously just to kind of like get you started, get you, get you working with it, not necessarily grasping all the concepts, not necessarily getting everything up front, but generally kind of how comfortable would you say you felt with like the project? Did you feel like you were kind of lost and you were basically just copying and pasting code, but not really knowing what it was? Or do you kind of feel like, oh, I'm starting to get it? Okay, well, you are an opinionated bunch today, so that is good. Well, Savannah clearly wasn't a fan of it. I think that much is obvious. Assuming you can hear her. So obviously that one's done. Homework 1, so originally obviously it was due this past Thursday. We extended it till Tuesday. And so, yeah, hopefully you guys have at least started about that. I know we got some questions coming in about particularly Q4 and Q5. So we're going to talk through both of those today. And then as part of that, hopefully you guys are going to be well set. So let me just kind of, before we dive into the code, let me just pause here and ask, does anyone have any questions or anything that, before we kind of dive into material? Okay. All right. Well, then let's do this. You guys are so agreeable today, man. All right. So today we're going to do a subject near and dear to my heart, and I suspect most of your hearts. We're going to do avocados because, why not? Life is short. Have an avocado. So again, if you want to sort of follow along, the Jupyter notebook for it and the should be data, but whatever. They're both available in that directory. Feel free to download. Now we're going to do two things with this. We're going to do, we're first going to do a predictive regression. So kind of analogous to what we did in Project One and the sample thing. Again, just to kind of hopefully reinforce those things. It's a simplified, streamlined code base. So hopefully it'll help to consolidate your understanding of it. And then we're going to tee up a classification. So this is something that the professor started getting into Thursday's lecture, talking about logistic regressions. And this is really what the focus of Project 2 is going to be. So this is kind of just to tee it up. And by the way, one thing that I will say that hopefully kind of put your mind at ease with everything is the good news for this course is pretty much what you did for Project 1 is what you're going to be doing for the rest of the course. You're going to run through there'll be some, we're going to ask you specific questions. We're going to ask you to run different models, pull up different metrics, maybe do different visualizations. But basically what you did for Project 1 is what you're going to do for the rest of this course. Now, I have to caveat that by saying that Project 3, we may ask you to do something a little bit different, but at least for Project 2, it's going to be the exact same thing. It's going to be Python, Jupyter Notebook. So hopefully if you're not feeling great about like where you're at with that, you've got plenty of time to kind of get up to speed. If you're feeling great with that, then, awesome. You can basically just kind of float. Okay, so first, let's actually pull up our little notebook here, and hopefully you guys can all see this. So yeah, so I pulled this data from the Haas avocado board. And so we compiled it into single CSV. So the first thing is, so we talk about, I know we've talked about before, kind of like a data dictionary. And so here's kind of the relevant columns that we're looking at here. So there's a date column, the date of the observation. There's an average price, which is the average price of a single avocado during that date in question. There's type, so you can either choose conventional or organic avocados. The year in which the observation is made. The region, so city or region of the observation. Total volume, which is the total number of avocados that were sold during that day. And then we have these three sort of, I don't actually know what a PLU stands for, but essentially those are sort of those are three product labels. So I would assume it's equivalent to like a small, medium, and large sized avocado. So that's the data that we're given. So let's, without further ado, kind of just dive in here. So we're obviously going to import NumPy, we're going to import pandas, and then assuming you've downloaded it into the same directory, you just do a simple pandas read, and then let's just call the head function. We can see kind of what we're working with here. So we obviously have our date, average price, total volume, which again, total volume sold, the PLUs for the three specific products. We have data here around, I guess, bags sold, which I guess is looking at like in terms of bulk purchases, I suppose. We have types, and then we have regions. So as a next step, let's kind of let's pull an info and let's see what we've got here. So we can see here we have a number of floats, we have some ints, and we have a handful of objects. And bumping back over to here. So remember what we've talked about before, because most of these, virtually basically all learning models are numeric. They need to take numeric inputs, which can be either integer or floats. So, first thing you're going to do when you look at your data is if you see any objects, you're going to know that's a problem. And so we have to do one of a few things to them. One other thing that I'm going to kind of point out here is that when we first read in our CSV, so you notice that there's a date here. Now, right now that's just an object. So right now that's just a kind of a plain text thing. But you see it is nicely structured. And in fact, Python does have sort of a specific date format. And there's actually a really, really convenient pandas function that can sort of convert object structured date files into date files. So you see, if I do that conversion, I don't actually do it here, but if I did it and I pulled the info, you'd see now date is this date time 64. And I'm just kind of floating that out, not because I want to spend too much time there, but that's a really, really useful thing for a number of reasons. Date itself, you can't put into a model. There's a ton of useful features that you could potentially augment from it. So I just kind of like, particularly if you're thinking along the lines of sort of creating some time series type features, having that date time value is an incredibly useful thing to have. So again, just want to float that out. I don't want us to get too bogged down with that, but just kind of be aware that that is something that we can do with that. So, okay, back up to here. So now that we see that, so the next thing we want to kind of do is look for imputation. So there's another sort of nice, easy pandas function we can do, is null, and then sum. And so for each of these, we can, so remember, we also were able to do kind of the non-null here. And we can see here that these are all uniform values. So that tells us that we're probably looking at a comprehensive data set. But this will just confirm it. Look at that. No nulls, no imputation needed. Happiness. Okay, awesome. Oh, okay, here's my to date. So I did actually do it. So the first thing, so remember, we're going to do two things with this data. So the first thing is we're going to build a predictive model of average price. So, we want to try and, essentially, I think we're just going to do a linear regression for this and just kind of see how we do. So similar to sort of before, we're going to set our new labels, our Y set as average price. then we're going to do two things. So we're going to drop the average price from our data, and we're going to drop the date. Because again, for the sake of this, I'm not keeping date. There are ways to do dates, and you can you can convert it to, I forget what there is that numeric, there is that date standard that you can do that just kind of sets it as like a numeric value. And so you can have dates as an input to your model, but for our purposes, we're just going to drop it. And then we have our X. Let's take a look at it again. Okay, this is looking better. We have a bunch of ints, but we have two objects. We have type and region. So we are going to do, oh, let me just pause here because I have a funny meme. Okay, I'm gonna just skip ahead here. So if you guys will remember, very, very important, always remember to remove your label from your feature. It's one of those things that you would just kind of automatically assume that you would do, but you would be surprised how often that happens. And like, I'll be honest, when I was setting up some sample code for this course, I built a model and I was running my metrics and I was getting like 100% accuracy. And I was very impressed by myself. And then I realized it was because I hadn't dropped my labels. And so unsurprisingly, my model was doing very well at classifying itself. So yeah, so always make the effort to drop your labels. And then we sort of get into the pipelining step. And if you'll recall, the pipelining is just simply kind of taking all the steps that we want to do and just streamlining it into a nice, very simple function call that we can just kind of pull to sort of just get our data nicely aligned. So if you'll remember kind of how it's structured, sort of peeling the proverbial onion, we have sort of our final array that we output. And so we call our full pipeline, which is essentially our set of instructions, and we call the fit transform, and we do data. And now I have this added to array call because when I was doing it, for some reason it was outputting a little weird. So just to kind of make sure it output as properly to a NumPy array, I just kind of added that call. That's not always necessary. And in fact, in your previous project, it wasn't, but for some reason this was giving me an error and that just kind of patched it. So again, your full pipeline is kind of your set of instructions that you're fitting into your data. So you're calling the column transformer method, which again, you're importing, and then you're just defining your set of numeric and your set of categoricals. And so for these, I'm doing one hot encoder for my categorical features, which I defined here. For my numeric, I'm doing the numeric pipeline, which here, since I don't have to do an imputer, although I could just define it, but I didn't. So here I'm just kind of scaling my numeric things, and I'm doing it for the numeric region, which again is, I've taken my numeric features by dropping the specific categoricals and then just defining them as the list of columns for that. And so then I pipeline it, and then I just visualize it and output it. And then here's my nice, pretty array. So then my data is prepared. So sort of coming near to the end, we then do a train test split. So again, we're converting our data into training and testing data sets. Here we're going to do an 80-20 split. Remember, we've already defined our Y data, our labels, way up here. We have prepared all of our data. We do the split. And then one kind of sanity check that I like to do after I do that is there's a function that you can do in NumPy called shape that gives you sort of a nice dimensionality array for my arrays. And so you can see here, after I've kind of run my my features, I have an array that has 14,599 rows and 66 features. For the test data, I have 3,650 rows and 66 features. And then for my labels, I have a corresponding number of labels. So that's good. I have a label for every data. And then the other thing you want to look at is you want to make sure that your features are uniform across your testing and your training. let me pause there because I want to talk about a few things. So generally speaking, this is kind of a good sort of recipe for you guys to follow. So again, sort of as a to-do when you're processing your data, copy your labels, drop them from your data frame, then drop all the features you aren't going to use, pipeline the rest. And, we've talked about that already. You have to kind of look at your features, make sure that they're in methods that you can use, impute any of your missing data. You have to choose a strategy for encoding. And I know there's been some conversation about when is a good idea to use label encoding, one-hot encoding, ordinal encoding, like other options that you want. And you can kind of make the decision on scaling or not. Then you split your data, then you train it, test it, and score it. So we're going to go back to 5, 6, and 7 in a moment. But I do want to kind of talk to you about sort of an interesting side note here, because I think that this is, does drop it. Okay, so there's a question in the chat. Let me just quickly see here. If you impute by missing rows with missing features, wouldn't you want to remove them, the labels later on? Okay, so good question. So this is an interesting, so the first question from Ricky is an important reason for why, one of the reasons why you impute before you split. Because if going back to where are we here? So going back to our dimensionality here, if I first imputed, or sorry, if I first split my data and I'm sorry. Okay, sorry. Let me pause here. If you are removing rows, you do have to remove the row before you remove the label. You're right. So Ricky, thank you for calling that out. So yeah, so if you so this is an important thing to note here, because remember from your dimensionality, you don't want to end up in a scenario where you have more labels than you have rows. So if your chosen imputation strategy is remove the row that happens to have a null value, you do have to do that prior to removing your labels. So thank you for calling that out, because that is an example of when you'd actually want to break this. There are a number of reasons why you necessarily want to break this approach, but that's one interesting example. There's another kind of interesting example that I want to talk about here. In lecture, we talked a lot about some of the hazards you may get if you do a simple train test split. And can anybody kind of remember like some of the things that the professor mentioned in terms of potential issues? While I not so subtly begin eating my lunch. So yeah, so why what are some issues? So if we just do the train test split, what might be an issue with that?
There is a non-zero chance that your test split does not accurately represent the data overall.
Perfect. That's exactly right. Yes. So because we're doing sort of a random and arbitrary split, there's a good possibility that your data, so firstly, there's always the problem when you collect a data set, that to what extent your data set is reflective of the universe around you, right? That's always the problem that you're trying to address with statistics, is to what degree is your little sampling sort of a snapshot of the broader universe. But then within that, if you're doing a random split, it is, as you said, high, greater than zero chance that the split that you do is not perfectly proportional. And so there are a number of ways around that. And one of the ways that we talked about that we'll kind of circle back to when we talk about validation was the k-fold cross-validation. That was sort of an interesting way of dealing with potential sampling biases when you split up your data set. There's another way to do this, though, that's kind of interesting. And again, I wanted to mention this, not as necessarily something that you would have to do for any of your projects, but just kind of something to be aware of. Like when we talk about this toolkit of stuff that you can do, and that's what's known as a stratified shuffle split. And so the idea here is that you want to kind of define a feature upon which you want to make sure, even though you're randomly splitting up your data, you're preserving sort of the proper ratios for it. And so here's some sample code here. This was actually originally in the in the sample code that you had for the housing. So originally the code had you do a stratified shuffle split, but I thought that was a little bit too complicated. So I just dropped that in favor of a train test split. But, you know, again, so the sample code is here, but like, let me actually turn around and ask you guys this to kind of help to solidify this. Using our Airbnb example, so the data that you just worked on, what would you say is what would you say would be maybe a good category that you may want to sort of ensure that you have a sort of a representative sampling in your training and testing? Okay, from the data that you were just working out with Airbnb. So I'll just throw one out there for you. How about neighborhood? Ah, there you go. Okay, Rob, nailed it. Yeah, so neighborhood, right? So we had, you know, we had the 5 New York boroughs. We had Manhattan, Bronx, Brooklyn, Queens, Staten Island, you know, all the sort of the boroughs. And you could see a scenario in which if you did a train test split, what if your model skewed very heavily to Manhattan when you trained? Well, naturally, your model would probably sort of bias towards a higher rent estimate. Conversely, if your model just happened to randomly pull a lot of Staten Island listings, you know, chances are you would go the opposite way. And so a stratified split says, okay, let's make sure when we're splitting our data, we're going to get a representative sampling of each of those boroughs. So I mention that because sort of an important thing when we talk about like the order in which you would do things. In that case, you would not want to pipeline your data first. Okay, here's a slide for this. So, because if assuming we're doing a one-hot encoding for our neighborhood, the moment we do that, we lose the ability to stratify, because we've essentially sort of taken that and created, you know, a series of binary features. So we don't have that ability to split anymore. And so if we did something like a stratified split, so going back to this example here where we kind of do this thing, in that case, we would want to actually split our data before we pipeline while we still have those nice categorical features sort of unmessed with. And then once we've already kind of split it, then we would pipeline both our test and our training data. So that's one example of why you would split your data before you pipeline it. And it was Ricky also who gave another great example of this. If you happen to be removing rows, you have to, you know, you have to pipeline before you split. So then the question is, okay, well, why not always split your data first? State 42. Okay, so let me just catch up on the questions. So there was a question as to whether or not removing columns is considered a imputation strategy. So it's vague and it depends on how you define imputation. I tend to define imputation very broadly as a generalized strategy for dealing with null values. And so from that perspective, I would count removing columns and removing rows as an imputation strategy. I know maybe like more strict definitions maybe wouldn't treat that technically as imputation, but I would treat it that way. And for what it's worth, if on a hypothetical homework question, if you were asked about imputation strategies and you just happen to use those, you would get full credit. Okay, and then there's the question about random state 42. Yeah, so it's just your seed. Obviously, for those in the know, 42 is basically the answer to everything in the universe. But that's just your seed. That ensures that even though you're doing a randomized function, you're going to get a consistent random generated output. So if you rerun your models, if you have other people run your models, you'll get the same split, and theoretically you should get the same results. So any other questions? I know I've been throwing like a lot of info at you guys in a relatively short amount of time. It's all the caffeine, man. I'm talking fast today. I've got about 3 coffees in me already. So any questions in terms of what we've covered so far? What does bucketing mean? Yeah. Okay. Thank you for asking to clarify that. So bucketing, if you imagine visually, you have like a series of buckets. It's the idea that you want to make sure that your sampling is distributed thing. So I also sort of had this this notion of like dealing a deck of cards. But essentially the idea is that as you are, so in this case, like with neighborhoods, as you are dividing your data, by neighborhood, you may want to like shuffle it up and say, okay, well, I have 500 Manhattan, 500 Brooklyn, 500 Bronx. Okay. And then of those, make sure a proportional number of those are, so if it's an 80-20, 400 go into training, 100 go into testing. So that's the notion of bucketing. It's not necessarily a formal one, but again, that's just kind of saying, if you know that there are categories that are important, and then you can, again, you can sort of be strategic. You don't have to be purely randomized. You could say, okay, well, within that you can be random, but I want to at least make sure I'm preserving those overall ratios. Okay, so there's a question about the imputation. So again, just to kind of confirm with the imputation, I don't know that there is like an official canonical formal Oxford English Dictionary thing for what counts as imputation or not, but I was saying that in my opinion and for the purpose of class and homeworks, any generalized strategy for dealing with null values, we're going to consider an imputation strategy. So the specific questions were around removing rows, removing columns. So yeah, if you do any of those will be considered 100% A-OK for your data and imputation strategy. So here's another kind of interesting thing that I wanted to mention in terms of like why you wouldn't necessarily want to split your data first. And that's a dimensionality mismatch issue. So let me pop over here. And so if you recall, one of the things I did after I did the train test split is I wanted to do the shape. And I said it was important. You want to make sure that your labels between are equivalent. So you have a label for all of your data. And then I said across your training and your testing, you want to make sure that your feature columns are identical. So hypothetically, how might it come to pass that you would not have an identical number of features across your columns?
What if we are doing one-hot encoding and one of our features is, I don't know, the color? In the test set, we have all 7 colors of the rainbow, but in the train set, we somehow are missing blue.
Yes,
That
yes,
means we
yes.
have one less feature in the train set.
Perfect. Yes. Okay. So that is a perfect example of this. When you one-hot encode, your one-hot encoder evaluates any data frame it receives naively. So there's no prior knowledge of any other data frames it's worked with. And it also has no knowledge of what the total number of unique column values are that it's supposed to be dealing with. So essentially all it does is it does for each categorical, it just reads it and finds all unique values that happen to be in that data frame. And then it assigns a sort of a binary feature for that particular value. So the example you gave is a perfect one. Let's say I split my data first and I have a column and I have a categorical. Now my training data happens to have all 6 or all 7, if you use your example, colors, but my testing one only has 6 out of the 7, which is not crazy given that you're doing an 80-20 split. If I then pipeline those separately, it's going to generate one additional feature for my training data that isn't in my testing data. Does anybody kind of see how that can arise, how that can potentially happen? So that's a scenario in which you would want to, if you're going to be one-hot encoding, you would have to one-hot encode before you split your data. Otherwise, there's a very real possibility that you would encounter that sort of that dimensionality mismatch. Now, having said that, you can potentially fix that if you do a stratified shuffle split, right? Because if the feature that you're worried about that mismatch, if you happen to stratify on it, then you know you are going to get a representative sampling in both your training and your testing. So in that case, it would potentially address that issue. So you could then theoretically split and then pipeline, but it is something that you need to be aware of. So these are all kind of weird considerations here because I gave you this like, hey, here's a nice like instruction thing for you to kind of how to process your data, right? And then I just spent the last 20 minutes telling you why this entire dude certified best formula for processing your data is just riddled with exceptions. But hopefully it's kind of giving you guys a bit of an impression about like all the kind of choices that you as a data scientist have to make when it comes to preparing your data. Because there really is just a lot of nuance and a lot of, again, kind of differing approaches that one has to take to getting there. So, okay, yeah, and so then there was also the example of obviously if you drop a column for imputation. There's another example, right? If your strategy is to drop a column and then it happens to be, for instance, that your test data happens to have null values, but your training data doesn't, you'll drop that column in your testing features, but you won't drop it from your training ones. So that's another really great example of precisely how you can get that dimensionality mismatch. Okay, but back to our data. Good news is we pipelined it. We output a very nicely scaled array. We did our little shape tests. We can see here it's a nice symmetrical feature set. Okay, we've got everything. So we then, again, this is pretty much just the code you ran for project one for the linear regression. You defined your model. You then set your model equal. You ran the fit thing for your training and your labels, and then you generated a set of predictions. And again, for the predictions, a nice, easy sanity check just to kind of make sure everything is working roughly the way it should. I just output the shape, and assuming everything worked well, it should equal your testing, your Y testing shape, right? Because you're generating a series of predictions for your test data, and you want there to be a one-to-one correspondence with that. So that's a nice basic sanity check to say, oh, okay, yes, this is run, but I do kind of want to make sure I'm outputting something that makes sense. The final kind of step for us, we want to see how we've actually done. So the first thing, it's very easy, right? So scikit-learn has a lot of great metrics libraries that are sort of just pre-built with it. So in this case, we can just import our MSE, we can input R squared, and then literally MSE, you just call the mean squared error thing, your Y test and your predictions. Same deal with R2 score, you just call that function, your Y test and your predictions, and then you just print the outputs. And so let's look at how our model did. So MSE, pretty good, right? Not a whole lot of variance. This is average price, and I believe average price is in terms of dollars, right? Okay, so if our average price is in terms of dollars, and our average price is about, let's say, $1, roughly around $1 or $1.10. If our mean squared error is, well, let's look at our RMSE. Our RMSE is about 30 cents. So that's not particularly great. That's not really horrible. If your average is hovering around $1.20 and your RMSE is 30 cents, that I wouldn't cache that model and retire on that, because clearly you got some work to do, but it's not the worst thing either. And then of course our R2 score. So that tells us a little bit more. So again, not terrible. We see that we have a 0.56, which tells us our model is capturing some of the variance in the data, but really not a whole lot, right? We're capturing a little more than half of the variance, but there's a lot of the variance in price that's going unexplained, which, judging by the magnitude of the error we're getting, Okay, that sort of makes sense, right? So that, in short, like really, really long story short, is kind of how you would do a predictive regression. So how's everyone feeling about that? I will take your silence to be joyous assent as you have feel completely and fully enlightened as to the nuances of creating these data models. Hooray. Okay. So, all right, deep breath, let's reset. Now we want to try to do something a little different. We want to try to do a classification. So this is a concept that the professor already kind of began to tease in lecture, but this is sort of a fundamentally different type of machine learning exercise than a predictive regression. And can anyone here sort of help to sort of clarify the difference between a prediction and a classification?
Well, shouldn't
Okay,
classification be a type of prediction?
Oh yeah. Okay. So
Right.
fair enough. So I think, all right, fair enough. So classification would be a subset of prediction. That's fair. But I guess the difference between let's just call it a numeric prediction versus a classification. Okay. So I'm seeing classification is categorical, prediction is continuous. Classification is a finite amount. Good. Okay, perfect. Yeah. So I'm getting some really good responses in the chat. So exactly right. So in classification, what fundamentally distinguishes it from a generalized predictive model is that there are a finite number of possibilities. Well said, Jacqueline. And also the notion that it's a categorical approach. So, fundamentally you're dealing with a discrete set of values, and you're trying to sort of match your data set to one of those values. So this is a very, very common type of machine learning exercise. The sort of famous image data sets, cat and dog, labeling. I know the professor talked about healthcare analytics. There's a lot of that there around like disease detection, whether or not a person, in fact, probably for project number 2, you're actually going to look to do something in healthcare. So we're probably going to give you a data set, assuming we sort of modify the project that was offered last time. We're going to give you a data set of patient with some like healthcare vitals for them. And then we're going to ask you to try to sort of diagnose just from the data whether or not they have a particular heart condition. So those are kind of examples of classifications. So here we are going to classify by the type of avocado. So we want to try to build a predictive model based on this exact same data set. We want to try to build a predictive model for whether or not the avocado is conventional or organic. And just looking at this data model, what do you guys think? Do you think we're going to be able to do how good do you think our chances are? Because when we did this prediction, we didn't do too hot. How well do you think we're going to do trying to classify intuitively? So again, as a data scientist, the Avocado Board of North America comes to you and says, "Can you build a predictive model with this?" If you were a gambling person, what would you say?
I would say it would do well.
Okay. Talk to me. Why?
I assume the average price, especially for something like organic or not, would make a big difference because it's like a marketing thing.
Perfect. Yeah. So as we know, it tends to be a huge difference, price discrimination between conventional and organic. So just the fact that we have average price probably tells us that we're going to do a lot better, because that probably, if we looked at, in fact, I probably should have looked at this. If I ran a correlation, we would probably see a pretty strong correlation between type and average price. So yes, so that would probably be a thing. I would also say that probably the total volume sold is probably also pretty closely correlated, just because there's probably a finite amount of each product, at least in terms of, even if the specific numbers will vary week to week, you could assume that overall volumes will probably be pretty consistent, right? You can assume that there's probably sort of a relatively fixed amount of organic versus conventional. And so we could probably see that in terms of the volumes as well. So, and then there's a question, right? Maybe because we're going to do a little better, just simply because there's a binary choice, right? Even if you're, if you're looking at a predictive, if you're looking at a prediction where there's an infinite number of values, it's obviously much easier to kind of get it wrong. Whereas if you're looking at, this is what's known as a binary classifier, it's a yes or a no. Well, even if you're just flipping a coin at it, there's a 50-50 chance you get it right. So chances are that, and by the way, I will note that one other kind of thing that's kind of important to note here is that the metrics that we use to judge classification vary specifically. And I dropped off early on Thursday. Did the professor start talking to you about metrics for classification? Okay, well, you were clearly following the professor's lecture with rapt attention. But I mean, we'll probably spend a lot of time talking about how you assess, much like we did with just kind of regular predictive scores. We're going to talk about some specific metrics for classification exercises. But one thing that I will note is that it's less ambiguous, right or wrong, right? For this, I mean, assuming your model isn't 100% accurate and predicting it well, we're really looking at that gray area, right? There's going to be like, if this is your real data, there's going to be that kind of gray area where if you're close enough, the model is good, but it doesn't have to be perfect, as long as it's like within whatever your sort of comfort area is. Whereas with classification, there is a very obvious right or wrong. You are either 100% right or 100% wrong on a particular label. And so there's less ambiguity in terms of what is or isn't a good classification thing. Now, we're going to get into it. There's a lot of nuance there too, but just so you're aware, kind of the way in which we think about the success of our model is fundamentally different than this. We don't really talk in terms of R2 scores and MSE scores when it comes to classification exercises. Just, again, kind of something to be aware of. So let's see what a classification thing will look like for us. So the first thing we want to do, so if we want to classify by the type of avocado, let's look at our discrete things. So again, another really kind of nice pandas function that you can do is for data, I can pull, I can sort of pull up my column type and then return the array of unique values for that data. So here we can see there's just two, conventional and organic. Okay, that looks good. By the way, I'm just going to kind of, one thing to throw out there. So we know that this data, so we have here, including sort of our ID column, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 13 features, including our ID column in our original data frame. Now, when we one-hot encoded it, we jumped out to 66. We went from 13 to 66. Now, one thing that we may want to think about is when we talk about our approach and whether or not it makes sense, for instance, to do one-hot encoding, is it good that we end up with 66 discrete features in our data frame? What do you guys think? Here, let me just restart and run all for this because I don't know if I ran this today. I'm going to quickly run this. So, and again, this is something we're going to talk a lot about. Okay, good. So that all worked. But one of the, this is something that the professor had sort of begun talking about. We're going to spend a lot of time talking about this, but if you have too many features, we start running into real issues around overfitting. And okay, good. Excessive dimension are bad. Yeah, model speed is important, but then again, overfitting is going to be another big issue. And we're going to kind of dive into a bit more about why that is. But just so you're aware, generally speaking, as the dimensionality of your data increases, your training output tends to improve, but your testing performance tends to worsen because you tend to overfit to your training. If your dimensionality increases too much. So, and in fact, so looking at our data here, so if you remember, we did type and we did region. Well, I am willing to bet data and region unique. Let's just call that, and let's just see what happens when, where's my little run bar? Why is it not? That's weird. Because am I on full screen? Is that why it's letting me actually run it? Well, that's annoying. Okay. Where did it go? Here, so I want that one. I don't know why it's okay here. So yeah, so when we hit this, look at the number of sort of discrete things we do. And I think, can I just do a count for this? I forget if this works. This might not work, but okay, no count. Okay, there's a way of just summing up your attributes for that too. I may have to look that up. But as you can see for region, unsurprisingly, we have a ton of distinct regions. So getting back to your decision, when you look at that, you may want to look at that and say, you know what, maybe I don't want to one-hot encode that. Maybe I need to do something a little bit different with that data. And there are a number of options that we could do. So one option is maybe we could concatenate this data. Maybe we could sort of do it regionally. So compress these from these sort of individual, basically, essentially city and region thing to maybe broader regions. So maybe we just do 4 or 5 regions of the country and just kind of concatenate these things. Maybe we just decide that there's not enough value in it and we just drop it. But the point is, when you see a categorical feature that has a number of unique options like this one, you may decide, you know what, it's just not worth it. That if I one-hot encode that, that's going to lead to a ton of overfitting. So again, just kind of something to be aware of with that. Oh, uniques count unique. Okay. Oh, awesome. Okay, guys, if you look at the chat, Tien has code that you could use to do that. Thank you, man. So, all right. So running through this again. So now I'm gonna kind of go through, and you'll see these steps pretty much are equivalent to what we ran for our regression. We're going to start exactly the same thing. We're going to remove our labels, but in this case, instead of removing average price, we're going to remove type, and then we're going to again drop our date. We're going to drop our type from our new features. We're going to sort of again pipeline it. But one thing to note here. So if you remember now, before our label was already in a numeric, but now our label is a categorical. So surprise, surprise, as the name suggests, one of the easiest ways just to kind of deal with that is to do a label encoding for it, because we want to change our label into sort of a numeric output. So here, and again, as the name suggests, and I saw in Piazza that somebody actually kind of flagged it, generally speaking, label encoder is used precisely for this reason. When you want to create when you want to sort of take a categorical set of labels and you want to create encoding for them, sometimes your label encoder is just the easiest way to do that. So that's exactly what we're going to do. We're going to import our label encoding. We're going to run the fit transform on it, output it, and suddenly we have this nice numeric one-dimensional array. Okay, great. So now we do the exact same thing we did before, our train test split. Let's look our dimensionality. And interesting enough, as you will see here, our dimensionality looks slightly different. We're at 65, whereas before we were at 66. Why is that? Well, obviously, we pulled out one of the variables that we had one hot encoded and replaced it with a numeric. And so because before this had two discrete values, it added one additional feature. So we went to 66. Now we don't have that, so it's only 65. So, but otherwise, everything's looking good here. And again, pretty much we've done basically exactly what we've done before. Yeah, so label encoding, all label encoding does is it essentially takes every discrete value in that particular feature and just assigns a number to it arbitrarily. So in this case, there are two discrete values, conventional or organic. It assigns a 0 and a 1. And then if there's multiple values, it will assign numbers to it, but it does it arbitrarily. So that's kind of something to note. It's an arbitrary assigning of values for it. And then it keeps it within that single feature thing. So, so rather than like one hot encoding taking every value and making its own binary feature, this takes that one feature and just kind of swaps out unique values for numeric inputs. Okay, so then no way to label encode. So there's another way to do it. I think it's called an ordinal encoder that allows you to do it. And frankly, you can also just do kind of a brute force find and replace. You can just kind of set things to it. Like if you do want to do this ordinally, if you do want sort of your either labels or a feature to kind of have a ranking, there is a way to do that. Yes. Yeah. So, so we did give examples of this. Last discussion section, we talked about sort of when it made sense to one hot encode and when it didn't. And we've already kind of shown one example here of when it doesn't make sense, right? When you generate features that are so feature rich that it kind of will lead to overfitting. That's one example. And then what was the other example of where it really doesn't make sense to one hot encode, even if you're dealing with a categorical? Okay, good. Yeah. So Drew, you're absolutely right. So when you want an association, so examples of that we gave were something like spice level. Let's say you're looking at a data set and where it has sort of different food items. And then it has, as part of it, it has a ranking of like non-spicy to very spicy. Well, you want, if you change that into a numeric, you want that to be maybe a 0 being non-spicy and a 5 being God have mercy on your soul, right? You want that kind of nice ordered pairing. You don't want it to randomly, you don't want your non-spicy to be a 3 and your very spicy to be a 2 and your mild spicy to be a 5, and right, like there the ordering is important. And this was something we had sort of talked about last week, that sometimes your data has those associations and you want to make sure that those associations are fed into your model. So another example of this is age. Age in this case is already technically a number. You can already fit it in. But generally speaking, somebody who is 79 and somebody who is 80 will have a lot more in common than somebody who is 20 than somebody who is 80. And so the last thing you would want to do is one hot encode something like age and just treat every age as a discrete sort of separate output. So that's an example where you wouldn't want, that's another example where you wouldn't want to encode, where that relationship is important. Because by doing that, you're effectively destroying that relationship and you are feeding essentially less information into your model than you should be. The flip side of this is true too. You don't want to do something like label encoding, something that's truly arbitrary, truly random. And we gave the example last time of neighborhoods, right? In the sample code that we worked through, at first we had several neighborhoods and we label encoded them. And so there was that, and so it output like Brentwood, Santa Monica, Westwood, it outputted numbers associated with them. And we said that was problematic because it suggested a relationship where it wasn't, and it suggested an ordering that we didn't necessarily want to make. We didn't want to suggest, for instance, that, Santa Monica was greater than Brentwood, or that, if we're going Westwood, Brentwood, Santa Monica, we don't necessarily want to suggest that Brentwood is closer to Santa Monica than Westwood is, even though actually geographically they happen to be. But the point is, like, we don't want to suggest that ordering where that isn't necessarily the case. So that's kind of one of the reasons why it's like important for us to kind of think through when we do these transformations to data, how we're impacting the model that we put in. And you don't just kind of want to get in the habit of just like, oh yeah, just one hot encode my categoricals, don't even worry about it. From an imputation strategy, just do this, whatever, just don't even think about it, right? It's important to kind of recognize that there are trade-offs with these things. And, and sometimes, like with these, like with these regions, well, region does matter to your model, right? Region does, prices tend to vary depending on where you live. So you may say, okay, that's important, but sometimes including a feature will introduce a lot of problems. And this is kind of an example of that. You may ultimately decide that a feature is more trouble than it's worth to keep. And you may have to decide to kind of drop that feature. But again, this is kind of getting into like the whole recipe aspect of data science, where there isn't always a right answer or wrong answer. Whether or not you would choose to keep region and what you decide to do with it, again, you just kind of have to play around with it. You have to maybe try removing it from your data frame and running the model and see how it works. Maybe try doing different types of transformations and running your model and seeing how it works. But, more often than not, you really don't know in advance what's going to work and what won't. And, and even though it generates a lot of features, if it gives you enough, there's concepts in statistics about entropy, the amount of like information, useful information that's conveyed by it. And if this gives you enough useful information, then maybe it's, even though it does have this downside, maybe the upside sort of overpowers the downside, if you will. So again, without playing around, you're not necessarily going to kind of know for sure. But yeah, let's bring this home. So you will see here, this looks, let's see. Okay, good. Yeah, no chats. Okay, so even though we technically import our metrics, we're going to do it again. And then we're going to import the logistic regression, which the professor talked about in class. But essentially, logistic regression is a binary classifier. So we define our model in this case, and we use like a particular solver function for it. We can get more into kind of what that is and what that does a little bit. Actually, also the homework 0 shows you a little bit of that. Then we also, just like with the regression model we did before, once we've defined our model, we then run the fit function on our training data, our training labels. Then that generates a set of predictions, which again is just we run that model on to predict our new on our new sort of testing data, and then we generate sort of a score. Do I need this score thing? Log reg predict probability. No, actually, I don't think I actually even need this line here. Score. Sorry, let me cancel this one out, because score is useful when we get into something called an ROC curve, which we haven't covered yet. We're going to cover, but we don't have that yet. So don't worry about score yet. But essentially, all you have to do with this is just call metrics accuracy score, and then you just have your predicted thing, and your predicted and your actual labels, and it returns an accuracy of 97%. So as we predicted at the top, unsurprisingly, given the data we have, we can build a pretty damn good classifier that can predict whether or not a particular data point is a conventional avocado or an organic avocado. But hopefully, as you can see, the actual sort of steps that you would take and the kinds of things that you would do, pretty much identical. I mean, the specific model that you're going to train, that's going to vary. The specific metrics that you're going to report out, that's going to vary. But the process to do it is pretty darn identical. And so when in project 2, you are asked to kind of do some classification stuff, this is pretty much what you're going to be doing. So let me see here. Do I have notes for this? I think I am. Okay, cool. Yeah, so that's what I've got for that. All right, let me kind of pause there and see how you all feeling about that. So, and let me ask you a little bit more generally, because I know, people were feeling relative degrees of confidence in terms of this process, in terms of the steps and everything like that. Are you, now that we've kind of gone through this, do you feel a little bit better about like the steps that you would take and why you're doing the things that you're doing and how it kind of comes together? All right, I'm getting one affirmative. Everyone else is sleeping. Cool. Well, hey, getting your sleep is important too. So if y'all catch up on your sleep during my discussion, then I will consider that a win as well. So yeah, if anybody has a question, feel free to kind of like jut in at any point. This is
I have a question about label encoding.
hit me.
So you mentioned that sometimes that if we don't want, well, I guess when you do label encoding, it still has like an association or ordering. It's just that the ordering is arbitrary, but it's still there, right? Like it's, like, I don't know if that makes sense.
Yeah, so there is an ordering, and that may or may not be important. If you're doing a binary classifier the way we were, for the most part, I don't think the ordering really matters. Like in our case, conventional to organic, you could maybe make an argument either way that maybe one should be 1, the other should be 0. But generally speaking, particularly when it comes to the your label where it has to be compressed to a single feature, in that case, you sort of have to, right? You sort of just have to assign the numbers, and there will be an ordinality to it, but that isn't necessarily the case. And one of the things that I will say is that I don't necessarily think, and you could even try this, you could try assigning 0 and 1 both ways and seeing if that impacts the model. But the reason I don't think it does is because when you're, and again, I'm going to use this nebulously, when your machine learning algorithm, when it learns a model of the data, it's not really learning anything about the label. It's only learning about the data that you're feeding into it, that your training features. So if there's a hierarchy to your labels, I don't think that impacts it as much. I think it's really just a, did you get this right or did you get this wrong? I think. But yeah, that is a good question. But I would say, simply put, if you're doing a binary classifier, generally, you probably don't have to worry about the order in which it is. And then even beyond that, because your model isn't really learning anything about the relative order of the labels. But is that true though? I mean, what if you're trying to do what if you're trying to predict spice level? Would it matter then? So, let me actually contradict myself here and say, if the order of your label matters, don't label encode. If the order generally doesn't matter, then label encoding is probably a good solution. So yeah, I hope that answers that.
Sorry. What if you had multiple label variables, but then basically it just corresponded to a binary number, and each binary number corresponded to a different category. So then it's like one hot encoding, but you still have that mutual exclusivity. Like you can't get 2 categories.
You'd have to clarify that. One thing I will say, there are more advanced sort of learning models that can try to do sort of multi-category labeling. but by and large, and in particular for this class, we're just focusing on sort of single label category, right? If you want to think of like a X and a Y model, there's just that one Y value that you're trying to build a model to predict. Now, again, there are more advanced models that can take multiple labels as inputs, but at least for our purposes, we're really just looking at that one output, that one sort of Y value that you're trying to predict or classify towards. I don't know if that answers your question, but if you were in a scenario where you would have sort of, like for instance, let's look at like region, where you have like Atlanta, Albany, whatnot, you'd probably kind of want to maybe concatenate those into Southwest, Southeast, Northeast, Midwest, Northwest type deal. And then just kind of have those as your labels, maybe. But I will note it's not a bad thing to sort of ask these questions about the labels, because on the one hand you might think the labels are the most obvious part, right? You might say, well, what I do with my data, okay, that's a bit up in the air when I want to encode, but like the label should be the obvious part, right? What the correct answer is. But the truth is it can actually be really difficult. And I'll give you an example of this. So we did a study, a classification study, where we were trying to predict the mental health of an individual. And the data that we had collected so we had our labels were survey results that people were submitting. And so, and the standardized test scored into 4 possible outcomes. It scored into, I think, healthy, mild, stress, moderate, or severe. So we had sort of a healthy thing, and then we had various stages of mental duress. So we actually ran a few different classification exercises. We ran one where we ended up actually dropping severe because, and we'll get into some of this too, but we had an unbalanced data set where we had a lot of healthy and only like a handful of mild and moderate, and basically like 2 or 3 severe. So like our data was so skewed, we couldn't really even use the severe. So we ended up dropping that from our label. So we did a 3-tier classifier. And then we also just did a binary classifier where we collapsed all of our kind of distress labels into a particular like healthy, unhealthy, and they ran a binary classifier for it. So all of that is by way of me saying, like, it's not actually crazy to spend a lot of time thinking about your labels, because as a data scientist, part of your job may also be to kind of figure out precisely the question that you want to answer. And kind of figure out like what the data gives you. Like it's in that case, we unsurprisingly, because our data was so unbalanced, we did a better job with a binary classifier, a very simple, healthy versus distressed classification than we did trying to sort of tease out the nuance of a various level of mental distress. So, if we had just stayed with, for instance, trying to bucket it, we may not have actually kind of gotten really useful features, but by sort of reframing what we were trying to do, we were actually like, oh, okay, we can work with this model. Maybe it doesn't give us the granularity we want, but this is actually useful. This is something we can work with. So it's definitely not at all bad to be thinking not just about everything that you can do with the X's, but what you can also do with the Y in your label, in your data as well.
Thank you.
Yeah, so really great question. So any other questions, I guess, about like any particular steps that we took with this exercise? Again, I hope the code is useful. Please feel free to download it. Feel free to use it for project 2. Again, however it can be helpful, please take advantage of it. Okay, so then let me run through a little bit. So for the rest of today, just to kind of take stock of things, I want to kind of run through a bit of homework 1, and then we'll specifically, I'll kind of try to answer some questions that I can, but I also want to kind of talk a little bit about questions 4 and 5, because I think a lot of people have questions about that in particular. And then just see if you guys have any questions. And then I'm hoping at least for the last 20 minutes or so, I can kind of break you guys out into breakout groups. So that's my plan for the rest of the discussion today. But you guys doing well? Do you need a breather, or you should we press on? Okay, I'm just going to assume we're going to press on. Okay, cool. All right, so homework 1. So one thing that really important is in the resources thing under CCLE. There's a resources sort of, I guess, page, and as part of that, so every week there's sort of like a really good set of just coding examples, coding labs that another data science course, I think it's actually the Harvard Data Sciences course has. And so we kind of have pulled that, and we've been adding that there as sort of an additional reference for you guys. And so one thing, if you haven't looked at it yet, is to go specifically into this Homework 0 Week 2 library, because this is, so I have it here. It's a really useful thing for both linear regression and KNN, and pretty much gives you, it does have like a ton of really useful information. It talks a little bit more about like it starts here about talking about like NumPy and sort of and arrays and things like that. It talks a bit about doing different plots with matplotlib. And you can see kind of different types of activation functions for it. This is for like the logistical regression, which we covered in class. Kind of shows you how to do a linear regression, which hint, 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 question 5. This is, this is pretty much what you would be using for that. And then let's see, yeah, but we'll kind of go through this. It shows you how to pull up a lot of good statistics like p-values, r-squared, f-statistics. It just kind of shows you how to just generate those values. And then it also gets into KNNs, which we'll talk a bit more about, but kind of walks you through code that you can run to get that as well. And then last but not least, it just gives you the code that you would need to run to do the bootstrapping example. So if you have not already downloaded that, please do it. I mean, basically, pretty much everything that you would need to solve those problems is going to be there. Having said that, I did put together some notes specifically around KNN. So I do kind of want to run through that because hopefully I think maybe there's a little bit of confusion as to like how a KNN works, what it is and everything like that. So I did kind of feel like it might be useful for us to talk it through. If it isn't, feel free to tune out for the next 5 minutes or so. But so here's kind of I guess an interesting thing about KNN that makes it different than other models that you're going to learn. And so, I mentioned, and again, I use this term and we haven't defined it explicitly. So you don't really kind of have a good grasp of when I say that your model learns your data, we haven't really talked about what that means. But here's kind of an important, so an easy way to think about it is your linear regression, right? We have a set of data. What your model is learning is the coefficients. It's learning sort of a transformation that it does to your data. So that's the thing that it is learning. That's the active learning step. A KNN is fundamentally intrinsically different in that there isn't an explicit learning step. There's no learning for a KNN. Right? KNN literally means just take whatever your K nearest neighbors are and then assign your label based on that, which essentially means that your model is your data set. Right? Whatever your training data set happens to be, training is even the wrong word to use there. It isn't that there's a training data set. Your training data set literally is your model. Every new data point that you come in, your test thing, you're just simply plugging it in, seeing what the closest values are in your training thing and returning a result. So again, it doesn't really do anything for it. It doesn't learn anything. It doesn't alter any coefficients. It doesn't, right? So it just kind of takes the data that it's given and just returns its nearest neighbors. So so that's kind of, again, something to note that's just fundamentally different about how k-nearest neighbor works versus basically any other type of machine learning model that you're going to learn in this course. So, as we've noted with like a k-nearest neighbor, it essentially works very simply. Our data, again, just becomes loaded into the model. We specify what the number of neighbors we are, then we have our testing thing. And then whenever we input our data into it, we just kind of look at what the number of nearest neighbors is to it. So I think you can't necessarily see this very clearly, but so if this is our test thing, we literally look at the 1, 2, 3, 4, 5 nearest neighbors around it. And in this case, we're doing a classification exercise. So in this case, we would literally just do a, whatever majority rules. In this case, it's green. It's 4-1. So we would say, okay, we're going to assign green to this label. Now, in the case of a prediction, where it's not just a binary classifier, what we do is something a little bit different. What we then do is we take the average value of the nearest neighbors. In this case, we would take the average Y values of these neighbors and use that to assign our sort of the weight to this. Let's see, we already talked about how it doesn't learn a model. We already sort of talked about how it's like a just-in-time by just calculating that. And again, your KNN, because your training set is your model, it just stores the entire data set when it uses it for it. So just kind of put this into perspective. I think it's always kind of useful. And we're going to talk about this a bit more as we begin to learn different models, but just kind of thinking about like why you would want to use a KNN, why you wouldn't. And so there are some very obvious advantages to it. The first being that because there's no explicit learning phase to it, you can begin classifying immediately. And in many ways, it's kind of like a first pass model. Like sometimes a data scientist, if they're interested in kind of just seeing something, they may just pass their raw data through a KNN and just kind of like see what happens with it for precisely that reason, because it gives you just information right off the bat without really having to do anything with it, which again can be really useful. It also is like can be really, really useful in terms of just understanding how your data is structured and kind of how well, right? It kind of helps you sort of understand how distinct your data is, how nicely it's divided, whether or not it's linear or it's a non-linear, but it clusters or that, right? It can give you some really good insights into your data structure. It also tends to perform reasonably well. I mean, when you throw it up against some of the other kind of classifiers, it does like its performance is remarkably solid, just given how simple it is. Another thing that's really important is that a lot of classifiers work around sort of linearity. Like you want to be able to kind of divide your data into like what we call like a linearly separable plane, right? If you imagine you have your data arrayed in a multi-dimensional space, a lot of classifiers work by like trying to like cut the data literally in the middle and then try to like say which side of that data your thing falls. And so that works really well if there is that linear separability. If there isn't, it can be difficult. KNNs, because it just looks at proximity, it works great with nonlinear data that just doesn't have that kind of nice thing too. So examples I gave of this are, so types 1 and 2 diabetes. So let me, does anybody kind of know medically what the difference between type 1 and type 2 is? Okay, good. So type 1 is genetic. Okay, so let me even take a step back. What is diabetes? If you ever saw those ads. Diabetes. What is diabetes? Okay, we clearly have a lot of pre-meds in this class, don't we? Okay, so I'm seeing here, okay, Problem's good. Good. Problem with pancreas producing insulin. It's not great. That's true. So it's a little bit more nuanced than not producing insulin. It's also known as insulin dysfunction. So oftentimes your body can produce sufficient quantities of insulin, but sometimes it doesn't produce enough insulin, but it can also produce enough insulin, but the insulin that's producing is essentially dysfunctional. It doesn't work effectively. But yeah, insulin is a molecule in your bloodstream that helps to regulate blood sugar content. And so if you're diabetic, your insulin, either for lack of producing sufficient quantities or producing ineffective quantities, just kind of stops regulating your blood sugar. And as we noted, there are two types. And so Dan is correct. So type 1 is genetic, right? So you can have people who are just born with insulin. They can be very young. They can otherwise be very healthy. They can look, thin, everything like looks good, but they just happen to be diabetic. Okay, what's a type 2 diabetic then?
Not when the insulin becomes like less effective, and so it doesn't effectively take the sugar out of the bloodstream. So then the pancreas has to keep producing more insulin, and then eventually the pancreas like just gets overworked and can't produce insulin, and then you have to get insulin shots, right?
Perfect. So, and who does that type of diabetes happen to usually? If you had to think about like your generic person who suffers from type 2 diabetes, what does that person look like?
Adults.
So, okay, I can just throw this out there, right? Generally, those people are older. Generally, those people have comorbidities. They tend to be overweight. They tend to have issues like heart disease and other things, right? They tend to have kind of issues with weight, lifestyle issues, poor eating habits chronically that have kind of led them to consuming just too much sugar that, again, over time kind of degrades the body's ability to process it. So essentially that's, I don't want to call it a lifestyle disease because, I mean, there are real medical issues that can kind of cause it and things like that. But generally speaking, if you think about like the profile of the individual, they tend to be older, less healthy, a lot of comorbidities, a lot of diseases. So why do I mention that? So if you imagine a data set of type 1 and type 2 diabetics, and then I was saying, hey, let's do a binary classifier for, is a person diabetic or non-diabetic? Well, you might imagine that you're going to get in this corner, you may get the cluster with a bunch of type 1 diabetics. And then in this corner, you may get a cluster with a bunch of type 2 diabetics. But there isn't kind of a nice linearly separable plane that will do it. So things like a logistic classifier, things like an SVM, those models are not going to work great on that. But that will work. A KNN that just looks at proximity will say, hey, there's a cluster here and there's a cluster here, and that's fine. Because I'm just looking at its nearest neighbor. So it doesn't really matter to me if there's one or two or multiple different clusters. Like, I can work with that. That doesn't faze me at all. So that's, I think, hopefully that's kind of an intuitive example of where KNNs can be really, really useful in terms of working with data sets. And then just really quickly, disadvantages. So probably the biggest one is, like with a linear classifier, for instance, once you've trained your model, once you've learned the model, all you have to essentially store is the coefficients. Right? That's your model going forward, and then you just plug in the data and everything's good. So obviously with a KNN, because your training set is the model itself, it can become computationally expensive. And particularly the bigger your model becomes, the more and more difficult it is to scale something like that. The other thing that we noted, so remember where we talked last week about scaling and how important it is? KNN is the classic example of where scale becomes appropriate, because since KNNs just look at just the raw distance between things, if your various, so this is a two-dimensional thing. If this dimensionality is in terms of single digits and this dimensionality is in terms of millions of digits, then the only dimension that will matter at all for a KNN is this. Everything else is meaningless in terms of just pure Euclidean distance. So it doesn't correct for that. So that's, again, the good thing is it's naive. You can just plug in the data. You can see what works. The bad news is it for precisely that reason, if there's any kind of skewing, it doesn't tend to work well. Okay, so that's a lot, probably more than you wanted to know about KNNs, but hey, here we are. So there's kind of some interesting things that we wanted to talk about for KNNs, and this is called parameter tuning. And by the way, this is something that you're going to work on, that you're going to leverage extensively in your second project. So when I say, oh, I'm going to run a SVM classifier, I'm going to run a logistical classifier, I'm going to run a KNN, there's a lot of sort of tools, parameters that you can change in terms of your different models, and that will impact your outputs. And getting into question 4, this is one of the things that you're going to look at, is sort of tuning your parameters. And the most obvious one is the K neighbors, right? There's a reason KNN is not called 3-neighbor, 3NN, 5NN, 6NN. There's a reason it's called KNN. And that's simply because you can have, theoretically, however many number of neighbors that you want. And this is going to be kind of something that you see. So you will get different results depending on the number of K neighbors. So generally speaking, higher values of K will smoothen your decision boundaries, which kind of makes sense, right? Because the more sort of neighbors you have, the more your sort of thing will converge on averages, and the more it will, and the less variability it'll be. Because as you're, if you think about your space, like here, from like, let's say, from a certain point, like here to here, let's say that your neighbors won't change. And then the more sort of nearest neighbors you have, the smoother that decision space will be. And you can kind of see this here. Let me see. So this is like with a K of 1, where you're literally just choosing your nearest neighbor. You can see it's much more rigid, and it's really just kind of, with each point, it's sort of adjusting to it. Once you go out to K, you can kind of see that we're already beginning to see a decision boundary that is becoming much more smooth, much more regular. And again, getting into that sort of classic tug of war, overfitting and generalization. Generally speaking, we don't like models that are too, they're kind of too, I guess, balkanized, if you will, that are too fragmented, that are too kind of choppy like this. Because when we see something like that, we see that the model is, generally speaking, overfitting to the data, right? We're sort of getting a thing that kind of like the glove fits perfectly to the particular data set that you're working with. But the moment you kind of get out into the universe of data, suddenly that model really doesn't generalize very well. So that's kind of an interesting thing that we have to play with specifically with the KNN. And that's one of the things that you're asked to do for Q4, just to kind of, again, give you some context. The other thing to be aware of is weights. So this is also a really cool thing that you can do with a KNN, where you can kind of output it. Like sometimes you may want to do a higher number of Ks, but should all Ks be treated equally? Going back to our example here, so we have a K of 5. So, we know that our K is going to be 1, 2, 3, 4, 5. I think those were the 5 nearest ones. But we can see that these green ones are further away, whereas it's like really, really close to this one blue one. So just kind of visualizing like that, we might say, maybe we don't want to treat, even though we're taking all of these into it, maybe we don't want to treat them all equally. Maybe we want to weigh our Ks based on their relative proximity. So in this case, the fact that we have this blue one that's literally right next to it, maybe we want to weigh that a little higher than the ones that are further away. And so that's the idea of weighing. So you can, even though you're taking a higher number of Ks, you assign a relative weighing perspective so that it still kind of biases towards the ones that are sort of immediate next to it. And then just kind of one other thing to be notable is sort of how you calculate proximate distance. So the most obvious one is just doing a Euclidean distance, just kind of the relative distance between the points. There's also the notion of a Manhattan distance. Pop quiz, does anybody here know what Manhattan distance is? And why it's called Manhattan distance?
Yeah, it's when you take the distance as like the distance in X and the distance in Y, and it's called Manhattan distance because it's like if you're walking through Manhattan, you wouldn't be able to just like cut across buildings the way you would with like the Euclidean distance.
Perfect. Exactly right. So that was Rob, correct? Yeah. So perfect. And then Laurel in the chat also exactly. You know, thinking about like city blocks, right? Manhattan is famously this well, at least north of 14th Street is like this really nice grid, very kind of easy and intuitive to do. But exactly that, you have to move on this sort of 90-degree, either vertically or horizontally. You're not able to kind of cut diagonally across. So sometimes for your models, you may want to calculate Manhattan distances. Maybe just kind of depends on the particulars of the model that you're working with. Okay, so this is kind of obvious for like a classification. So here we're doing like a three label classifier. So how does it work for a predictive regression? So, and I actually stole this from here, from your little thing here. So again, kind of nice to look through. But as I noted, predictive regression works very similarly. All it kind of does is it says, let's take either the nearest point itself or the average of the nearest points. And then based on that, we use that to kind of predict the output. And so just kind of like as an easy example here. So let's look at this orange. I hope you can kind of see this clearly. So if we're doing just the one nearest neighbor, well, then the one nearest neighbor is whatever it happens to be closer to. It's basically immediately that point. So it starts anything that's closest to here is going to be that value. And then the moment, almost immediately, when it gets closer to this thing, it jumps up to that value. And so anything that has the X value up till here is going to be that value. And then the moment it gets closer to this, it jumps down here, that's small, there. So we can kind of see how if it's an N of 1, it becomes very choppy. Now, if we look at an N of 2, we can kind of begin to see a smoothing factor. So here too, you're looking at the average of these 2 points here, everything looks good. And then the moment it kind of hits this point, well, now the average is between these two. These are the two nearest neighbors. So now it'll be the median of them. And then at some point, as it gets closer to here, the nearest neighbor becomes these two. So it jumps to here. And at some point, so you can kind of already begin to see it smoothing out as it sort of has to, at every point, kind of take what the two nearest neighbors are and smooth it out. And then eventually, once you get to 15, well, now you can see that our formally rigid thing has already kind of begun to nicely smoothen itself out. And then, of course, so let me ask you this. If our KNN, if our K value eventually becomes just the entire data set, what does our predictive line look like at that point? Okay, well, I know you guys are thinking it'll look a lot like the mean, the average. Yeah, straight line at the mean, exactly right. So, if your entire data set, if it's the K nearest neighbors, if K is equal to your data set, then perfect. It's just your nearest neighbors. It's just the average mean line. So, so kind of getting into it. So hopefully, pausing there, hopefully that kind of gives you, I guess, the context you need to solve question 4. Because question 4 is actually not that difficult. It's just maybe conceptually it was a little bit kind of hard to understand what you were asked to do. But essentially for parts A and B, you're just going to simply plot the graph using the different K values. So I think you're first asked to do like the 1 nearest neighbor and then 3 nearest neighbors. So you're essentially just kind of asked to reproduce this graph. And then use that line to predict. And then for part C, I think for that you're sort of, so for that you're giving, so remember how we talk about our parameter tuning for K neighbors? So for that, you're given different K neighbors for your data set. You're asked, I think, like, I forget the exact numbers, but you're asked to sort of see which model will be better, I think for like 1, 3, or 5 nearest neighbors. And so for that, you just, simply kind of plot out those models, and then you can use any criteria. You can use an R2, you can use an RMSE, MSE, whatever you kind of want to use for your loss function. And then you just kind of calculate whichever one just happens to have the best output. And then for part D, I forget what part D is. Hang on, let me stop sharing for a second. What is part D? Okay, so part D is. Okay, so it just, yeah, so then it just asks you to solve, to calculate the R2 when your K is 1, and then just kind of think about why K equals 1 may not be a good model. And, you know, again, we have sort of already kind of hinted fairly strongly at why K may not be a good model, but again, just kind of going back to here and remember how choppy this is, remember how our decision boundary is kind of all fragmented and haphazard here, and maybe how that might be an issue with regards to, for instance, overfitting. So that's problem 4 in a nutshell. Then problem 5 also just will rely very heavily on that homework 0 code. So essentially, you're given a data set with sort of the following X and Y values, and then you want to fit a model. So part A just asks you to write down the updating rule. So based on what was described in class, do you guys have a decent sort of sense of what a gradient descent function is and how it works? Okay, so kind of really basically, and I am going to spend some time in a future discussion really getting into like loss functions and gradient descent functions and the whole process of like how a model learns. But the way of kind of, I guess, at a very superficial level, the way of thinking about this is a gradient descent function is kind of the, oh, hang on, Ricky, I'll take a look at your question in a second. So essentially your gradient descent function is a kind of like, it's a way of like directing your model is a way of thinking about it. So you have your loss function. That's essentially how you keep score, how you're doing. And then your gradient descent function kind of just tells you, rather than just jumping around randomly, you have to have like a systematic approach to sort of how you project. And so the gradient descent function really does two things. It sort of shows you directionally which way to move, and then it kind of sets the appropriate sort of, I guess, parameter to make that move, right? You sort of have to, if you've set your weights to a certain value, then you want to see, okay, well, that's not great. Let me try a different set of values. And there's that whole kind of updating policy. And there's also kind of a delicate dance there. And we'll get into that where like, you don't want to set your policy to be too small because then it takes forever for your model to train because it has to try all these iterations, but you also don't want to make it too big because then it can like overshoot what your actual optimal solution is. And so number 1 is just asking you for that updating function. And I think that's just very easy, just something you would look up. Okay, and so then for number B, again, just go and take the code that's in homework 0, and you can just use that to fit your model. But regardless, whether or not you choose to use that thing, just use Python for that. Don't try to fit your model by hand or do anything like that. That's just not. You're not going to be in for a good time if you do that. And again, for part C. So that's sort of the bootstrapping example. So here, I'll even just kind of show you like this is just straight up in the code. There is basically like right here, you have, the exact kind of parameters you would need. You already kind of have your model. You can kind of output your things directly. I mean, it pretty much gives you just everything you needed to solve that. So don't try to reinvent the wheel. You're given the code you need to do that. Let's see. So that's part C. Yeah, again, part D, the code is provided for you. Part C, part D. Yeah, your T statistic again, and your p-value. So you're given that just straight up here. Sorry, let me just share again. So, and he even mentions in the question prompt that there are sort of nice, easy libraries that you can do to kind of calculate that. But where is it here? Okay, yeah. So you can kind of just get, you can just kind of pull your result parameters. You can just output your regression or results, and they'll give you your F statistics, your R squared things. It'll just kind of give you this nice summary table that'll give you pretty much everything that you need in terms of your coefficients, and then your p-values associated with them. So yeah, it's like really nice, really easy, really simple. If anything, I would say like think about question 5 in particular is just basically being a coding question. It's just plugging those inputs into Python and getting your outputs. And then part 5 is just a little bit of a thinking question, but again, just kind of think about, you know, if your data set doesn't fit a normal distribution, like what are some things that you can do, right? So we have talked about overfitting, and we've talked about kind of things like that. Well, maybe if your data is non, you know, doesn't fit a normal parameter, maybe there are times when you kind of do want to take it a different way, and just kind of just thinking that through. But you know, obviously, sometimes a general model doesn't work for your data when your data doesn't follow sort of a nice generalized data set. Is maybe what I would say, to kind of think about that question in that way. So I know I ran through that. I know we covered like a heck of a lot of content today. Oh, ignore that. Oh my goodness, I should have updated that. I'm sorry. It is not due tonight before midnight. It is due next Tuesday. In fact, let me just fix that like right now, because I don't want anyone seeing that and freaking out. Tuesday, January. Okay, yeah, we're in this in real time. But so I know it's already pretty late. You guys have been troopers. I'm gonna sort of see if anyone has any quick questions, but I do kind of want to shout out because we have a really, really awesome meme this week brought to you by none other than Monik. So I will leave this here for you guys all to bask in its glory. And then I'll just see, does anybody have any sort of homework questions? Because if not, I'm going to break you guys into some breakout groups. And I figure maybe you guys can kind of start talking through some of the homework together. But one other thing I'd like to hear is kind of just what you guys are doing to, you know, what are your survival tips? How are you keeping sane this quarter? So yeah, if you want to kind of stick around for that, it'd be cool to hear that. But otherwise, yeah, let me just kind of pause there and see if there are any kind of questions or anything we want to talk through. Otherwise, I will kind of take the survivors and put you all into breakouts.
I have a question about something from like the beginning of discussion, basically.
Mm-hmm.
So you mentioned that you could get a dimensionality mismatch when you split before pipelining.
Mm-hmm.
I was wondering, couldn't you just run your pipeline on both the test and train data?
You would, but let me give you a specific example. So let's have a category called color, and it has red, blue, yellow, green as like discrete things. Imagine that I split my data into training and testing, and then testing, by nature of only being 20% of my sort of total thing, only happens to get red, blue, and yellow. Whereas my training data gets all 4, it gets green. So then when I run the pipelines on my training and my testing, when I run it on my testing, My one hot encoder will only generate 3 features for the red, blue, and yellow. It won't generate one for green because it doesn't know to do green. It doesn't know that there's a green out there in the universe. But whereas when it runs it on my training data, it sees there are 4 values, so it'll generate 4 features. So that's an example of how you would get a parameter, a feature mismatch.
Makes a lot of sense. Thank you.
Yeah, awesome. Okay, any other questions?
Oh yeah, sorry. I tried logging into the grade scope,
Mhm.
using the same link. It still kept sending me to another like classes.
Oh, well, that shouldn't
Oh,
be.
not sorry, grade scope. Piazza.
Oh, Piazza. Okay, so you're still having issues with Piazza. Okay.
Yeah. Oh wait, no, just kidding. It worked. It just, yeah. Sorry.
Yeah, it's
Wrong.
being temperamental. Okay, cool. Yeah, if you're not in the Piazza, definitely join. Ton of great questions, ton of great conversations there. If you're not in there, I would definitely recommend hopping on there.
Oh, and yeah. Sorry. Side question.
Mm.
Is there like doing data science? Like how familiar do you need to be with like neural networks and all that fancy stuff?
Yeah. So it's kind of the running joke about data science in that because as you see like with Python and libraries like scikit-learn and TensorFlow and PyTorch and all these things are like so well developed and so user friendly that it's very easy to kind of do it. I mean, you saw like in terms of we ran that classification exercise and the amount of like Python coding knowledge that you need to do to get that is incredibly low. And by the way, like a neural net is basically like in terms of coding difficulty is pretty much equivalent to doing the logistic classifier. It's literally as easy as just importing neural net and running it. And so it's the kind of thing where like there's a very low threshold to actually kind of generating data and generating outputs, but there's kind of that long tail curve in terms of like understanding how to really use it effectively and what works and what doesn't. And so, just as like an example, like we spent a ton of time today talking about, when would you one hot encode? When would you split your data versus pipeline your data? When would you do that, right? All of that is like the kind of nuance that comes from just spending a lot of time understanding the nuances of the models and the things that you're working with. So the short answer is, you really need very little information to kind of be dangerous in data science and like plug it in and get an output. But in terms of actually like being able to really use it effectively, there can actually, there is a fair bit of like knowledge, I guess, that underpins it.
Okay. And do you know if this class will be covering like PyTorch or
I don't think it will. I think like we've been talking about whether or not we'll use things like PyTorch or TensorFlow or libraries like that, or if we'll do other kind of data processing models like Hadoop or the short answer is I'm not positive we will. And that's just simply because there's so much information to throw at you, and we literally have 10 weeks, and our goal by the end of 10 weeks is to get you at least being able to do rudimentary data science, and there's just so much to cover with that. So at least when we taught it last winter, we just kind of stayed in the Python, Pandas, NumPy, scikit-learn, Matplotlib like space. We really didn't venture beyond that.
Oh, okay, cool. Thank you.
Yeah, absolutely. Okay, so then there were 2 of you. Oh, by the way, Joshua, were you the one who won the contest last week? You too, Monik. Thank you, man.